This is section 4.5, part 2, where we're going to learn how to rationalize the denominator. What does that mean, rationalize the denominator? Well, essentially it means to move the square root from the denominator to the numerator. All right, you want to take the square root out of the denominator. So, how do we do that? So this is essentially the same thing as what we were doing up here with the quotient property. So I'm going to scroll back up to what we looked at in the last part of our video. We had our quotient property, which said if you had the square root of some number, a fraction, alright, you could break that up into two smaller square roots. And so far what we've seen is the denominator was always a nice perfect square. Take the square root of 25, boom, it's 5. No more square root in the denominator. Over here we looked and we saw 36 was in the denominator. So square root of 5 over square root of 36. 36 is a perfect square. Boom, 6. No more square root in the denominator. But unfortunately, not every number is a perfect square. So we're going to have to rationalize the denominator sometimes if we want to get the square root out of the denominator. So how do we do that? Well, the first step is essentially the same, where we are going to break this up into two separate square roots. So we've got the square root of 7 over the square root of 3. And now we're going to really multiply by 1. But we're not just going to multiply by the number 1. We can manipulate numbers to make number 1 look an infinite number of ways. What do I mean? Well, we have 5 divided by 5 is 1. 10 divided by 10 is 1. 1,000 divided by 1,000 is 1. And 0.0001 divided by 0.0001 is 1. Really, anything divided by itself is going to give you the number 1. I've made 1 look like 4 different numbers, or it's the same number, but I've made it look 4 different ways here real quickly. So how do you know how you want to make 1 look? Well, it essentially is the number in the denominator. Square root of 3 is not a perfect square. You can't work with it. Alright, you can't just take the square root of 3 and get a nice number. Alright, because the square root of 3 is going to be somewhere around 1.6, 1.7, something like that. So it's not perfect. So I'm going to multiply this whole fraction by 1, and I'm going to multiply it by the square root of 3 over the square root of 3. And by doing that, this is the number 1. I'm not changing the value at all of this problem, but I'm going to change the way it looks. And I'm going to say the square root of 3 times the square root of 7 gives me the square root of 21. That's the product property there. Alright, two numbers multiplied together get you a larger number, or you can go backwards and break a larger number up into two smaller numbers. And same thing, square root of 3 times the square root of 3 gives us the square root of 9. And whenever you multiply a square root by itself, you're always going to end up with a perfect square. Always. Doesn't matter what number you work with. Alright, you're always going to end up with a perfect square. So what's the square root of 9? 3. And the square root of 21, you should look to see if it can be broken down real quick. 21, so you've got 1 in 21. Nope, that won't work. 2 doesn't go into it, but 3 does. 3 goes into it 7 times. And neither of these can be broken down anymore. So you know square root of 21 is simplified as it gets. And we've just successfully rationalized the denominator. Alright, we've gone from the square root of 7/3 to the square root of 21 over 3. And again, you can use your calculator to do a quick check. We'll take the square root of 7 divided by 3. And it's roughly 1.5. And then I'm going to take the square root of 21 divided by 3, and you see it's the exact same decimal, so you're confident that you simplified this accurately. Let's try another one. Let's come on down to the square root of 8/5. So I want to break this up into the square root of 8 over the square root of 5, and I'm going to multiply by 1 which is essentially going to look like the square root of 5 over square root of 5, and that's driven by what the denominator is. We know square root of 5 is not a perfect square, nor is square root of 8. Square root of 5 times square root of 5 is the square root of 25. And the square root of 8, to make things simple, we'll say the square root of 8 times square root of 5 is square root of 40. Or I can see 8, if you notice, 8 can be simplified. 8's got some numbers that can be broken down. So I can say, oh, 8 might be broken up into 2 and 4. 4 can be broken up into 2 and 2. I have two sets of 2. So this is going to be 2 times the square root of 2. So what I have here is I've simplified the square root of 8 to look like 2 root 2, and I still have times the square root of 5. So we know the square root of 25 is 5, and I can combine 2 and 5. 2 times 5 is the square root of 10, and this 2 here gets written right in front. And before you finalize your answer, alright, you should always look at, if you have a number that's not under the square root here, you should see if it can be simplified with the denominator. And we'll look at that more in class as well. Here, 2 doesn't go into 5, so we know we can't simplify this any further. Okay, so we're going to continue rationalizing the denominator, and we're going to introduce the concept of conjugates. Alright, what happens with conjugates? Alright, we'll see what that is in a second. Let's see. Well, let me scroll back up here. You can see that in these two problems, all we've had was a number down here. Alright, just a nice number. So you're able to multiply by square root of 3 over square root of 3. Sometimes you're not just going to have one square root in the denominator. You might have 3 minus the square root of 7. And you can't just multiply by the square root of 7 times the square root of 7 here because of this subtraction sign. You got to deal with the whole denominator. And that's where the concept of conjugates come in. Conjugates are pretty easy to form. So what we're going to look at is pretend these are 3 different terms in the denominator of our problem. To form the conjugate of the first one, 7 plus the square root of 3, all I'm going to do is switch the sign. Alright, if it's addition, we switch it to subtraction. If it's subtraction, you switch it to addition. That's it. And everything stays the same. So the conjugate of 7 plus the square root of 3 is 7 minus the square root of 3. These two are conjugates of each other. 2 minus the square root of 5, its conjugate is 2 plus the square root of 5. 12 plus the square root of 10, its conjugate is 12 minus the square root of 10. And then in order to solve these problems, I have a nice little note here. Alright, if we have 5 divided by 3 minus the square root of 7, to solve this, to rationalize the denominator, we want to multiply the numerator and the denominator by the conjugate. Alright, and so remember, anything divided by itself is 1. So we're essentially still multiplying by 1, but we can change the way the number 1 works. So what is the conjugate of 3 minus the square root of 7? Remember, all we do is change subtraction to addition, so the conjugate is going to be 3 plus the square root of 7. And that goes in the numerator and the denominator, so I have to put it up in the numerator as well. Anything divided by itself is 1. So now, the next step is going to be to FOIL the denominator. So I'm going to multiply 5 times 3 plus the square root of 7, and I'm not going to distribute the numerator yet. I like to leave this till the end, just in case it can get simplified. And here I'm going to FOIL the denominator. So 3 times 3 is 9. 3 times the square root of 7 is 3 root 7. Negative square root 7 times 3 is negative 3 root 7. And negative square root 7 times positive square root 7 is minus the square root of 49. Next, I'm going to simplify the denominator. And what do you notice about the middle two terms? I've got a positive 3 root 7 and a negative 3 root 7. So it seems like when I combine those, 3 minus 3 is 0. All right, and 0 times square root of 7 is 0, so these two terms are going to cancel. And when you multiply two conjugates together, the middle two terms are always going to cancel. And your last term is always going to be a perfect square. So I've got 9 minus, this last term is a perfect square. The square root of 49 is 7. Alright, so I've got 5 over 3 plus the square root of 7 divided by 2. And remember, I did not distribute in this 5 at all because I knew that my denominator was going to be simplified to one number. It will always happen when you multiply two conjugates together. Middle terms are going to cancel. This perfect square is going to be a number, and then you're going to be able to subtract these two numbers to get a final singular number here. And sometimes these two numbers will be able to simplify. So it's in your best interest to wait until you see what this number is to see if 2 can go into 5, which it can't. If it could, we would simplify first. Since it can't, my last step will be to distribute in the 5. So 5 times 3 is 15, plus 5 root 7 over 2. And there's your answer. Let's try one more. So we've got 2 divided by the square root of 3 times 5. Alright, we can see the square root of 3 is not a perfect square, so in order to rationalize the denominator, I need to multiply by the conjugate, which is the square root of 3 minus 5. So I have the square root of 3 minus 5 divided by the square root of 3 minus 5. This is equal to 1, so I'm not changing the value. I'm going to FOIL the denominator, and remember, I'm not distributing the numerator yet. I'm just going to leave it hanging out on the outside of the quantity, so that 2 does not get distributed in yet. That will be one of the last things we do. So the square root of 3 times the square root of 3 is 9, or square root of 9, sorry. There's our perfect square. Square root of 3 times minus 5, or negative 5, is negative 5 root 3. Positive 5 times the square root of 3 is positive 5 root 3. And positive 5 times negative 5 is negative 25. What did we say about our middle two terms? Middle two terms are going to cancel. So those cancel. I said the last term will be a perfect square, but it also really depends on where your square root is. In this case, it's the first term. Alright, so I've got 2 square root 3 minus 5. Alright, and in the denominator, square root of 9 is 3 minus 25. 3 minus 25 gives us negative 22. And I've got 2 times the quantity, the square root of 3 minus 5. And notice I did not distribute in the 2 yet, so I can simply see if I can cancel anything here. And it looks like 2 can go into 22 11 times, so it looks like I'm going to have an 11 in the denominator here. And then 2 goes into itself once. So 1 times the quantity of the square root of 3 minus 5 is simply the square root of 3 minus 5 over negative 11. So you can keep the negative down here. If you wanted to move it on the outside, you could. Either way, alright, there's your final answer. Okay, and that's the end of part 2.